Hello everyone, welcome to AAT Tech Talk. My name is Narala Siddhartha. My roll number is 20951A6744. My branch is Computer Science and Engineering with Data Science as specialization. So my subject is Computer Networks. So today I am going to discuss about 5G deployment, standalone versus non-standalone from the operative perspective. So let's start. So I mainly divided the content into four parts. In the first part, I'm going to give an introduction about the topic. So we are going to be discussed about the basic topics and fundamentals that are involved in this topic. In the second part, I'm going to discuss about the concepts of 5G, SANR and NSANR. And in the third part, I'm going to discuss about analysis of SA versus NSA. So in the last part, that is the fourth part, I'm going to discuss about the conclusions and the limitations that are going to arise in this particular topic. So let's start. Introduction. The fifth generation 5G mobile network is standardized and developed to explore the mobile market beyond 2020. In response to the diverse strategies of 5G deployment, five alternative network architectures have been proposed to 3GPP by different mobile operators. To fulfill the urgent deployment requirement from some operators, an early drop of 5G termed as non-standalone New Radio NR was completed at the end of 2017. After that, the standardization of a new 5G system, including the standalone new radio access network, was established and finished in June 2018. Okay. This article analyzes and compares the SANR and NSANR deployment modes in terms of coverage, network capability, interworking between 4G and 5G, complexity and cost of network deployment, and the latest industry progress. NSANR performs better in the interworking performance in the initial phase, while SANR performs better in working network capabilities, device performance, simple network deployment, and cost efficiency. 5G SANR is recommended for operators who have the ambition to explore new opportunities in the vertical and enterprise markets. The fourth generation mobile communication 4G, also referred to as a long-term evolution, evolved packet core LTE EPC, has opened opportunities for mobile broadband communication and played an important role in promoting new mobile services and applications. Some of the communication requirements of the new services and applications include enhanced mobile broadband EMBB, massive machine type communication MMTC, and ultra reliable low latency communication URLLC have exceeded the capabilities of 4G network. To address these new demands, 5G is being deployed and developed. To deliver the highly reliable, ultra-low latency, multi-gigabit connectivity that 5G portends, sufficient radio spectrum is a prerequisite. To offer premium 5G experience, a significant amount of new harmonized spectrum is demanded for the 5G network deployment. Ideally, 80 to 100 MHz of contiguous spectrum per operator in below 6 GHz bands and around 1 GHz per operator in millimeter wave bands. For 5G's nationwide coverage, spectrum band 2 GHz is also needed, especially for extremely low latency use cases. At the International Telecommunication Union (ITU) World Radio Telecommunication Conference held at 2015, that is WRC 15, some new bands below 6 GHz were identified for mobile services in different regions and countries with the range 3.3 to 3.4 GHz, 4.4 to 4.5 GHz, and finally 4.5 to 5 GHz. At WRC 19, which is held in 2019, Two new brands for mobile services were identified. Early rollouts of 5G in Europe and Asia will likely use spectrum below 6 GHz, while operators in the United States will remain start with the bands above 6 GHz for 5G and reform some 4G spectrum. With the guidance of ITU on technical requirements and evaluation methodology, the third generation partnership project began 5G standardization in 2015 and scheduled its first release of specifications on a 5G system in June 2018, including both the air interface and 5G core. However, as a huge amount of money has been invested to build a 4G network in the last decade, the mobile operators face a challenge to have sufficient financial support for large-scale 5G deployment. Because of the different forecasts on service opportunities brought by 5G and the concerns on the return of investment on 5G networks, many operators are pessimistic about launching a large-scale 5G network in 2020. Due to the different considerations on 5G deployment, five diverse network architectures for 5G NR deployment has been proposed to 3GPP by different operators, which may lead to fragmented 5G industry and market. On the other hand, the intense competition drives the operators to compete for regional leadership on 5G deployment. So let's discuss about the concepts of 5G SANR and NSANR. So what is 5G SANR and NSANR? In general, SANR architecture refers to a 5G system consisting of NR and SGC. NR is the control plane anchor, while NSANR architecture refers to a system that uses LTE evolved LTE as the control plane anchor for NR. Actually, both SANR and NSANR architectures consist of some variants. The five sets of architecture alternatives proposed to 3GPP are given in figure 1, with the option 2 and option 4 sets fall into the SANR category, while option 3 and 7 sets belong to the NSANR category. The difference between the options in one set is that option N supports a split bearer, option NA supports a second cell group bearer, and option NX supports an SCG split bearer, where N could be 3, 4, or 7. So the network migration steps of NSANR and SANR are also illustrated in our understanding. No matter which one is deployed in the initial stage, the ultimate deployment mode is the same. When it moves out of NR coverage, the user equipment is handed over to an LTE network where UE connects to LTE EPC like a general LTE device. 5 network architecture options proposed to 3GPP and the potential migration paths. IEEE Communication Magazine, November 2020, 85 TL to explore the new service opportunities from enterprise and vertical markets. NSANR requires a device to support dual connectivity, which means the device should maintain LTE and NR radio transmission links simultaneously. Sharing of the total transmission power of device between the transmission links lead to more limited UL coverage than the LTE system and shorter battery life. In some paid bands for NSA-NR, interference between the two communication links may happen and lead to worse terminal performance. Analysis of SA versus NSA. Typically, to select one network architecture from 5 alternatives, many issues need to be considered. For example, radio coverage, network capabilities, terminal performance, 4G or 5G interworking, complexity of network deployment, and cost for further evaluation. Details of these aspects are given in the section. So, conclusion. 5G is designed to explore the new business opportunities of EMBB, MMTC, and URLLC scenarios. Five alternatives for the SANR and NSANR network architectures have been proposed to meet the demand of diverse deployment strategies. Okay, in this section, option 2 and option 3 are compared from the operator's perspective to facilitate the understanding of which one should be selected as the first step. This coverage, network capabilities, device performance, 4G or 5G interworking, complexity of deployment are analyzed in detail. From the analysis, it is proved that SA outperforms NSA in terms of device power consumption, network deployment complexity, and cost. NSA option 3 has some advantages in 4G or 5G networking and capex for the initial deployment. Thank you.